through these introduction slides. And we looked at our first examples of sequences. We just introduced this basic notation. Again, this is just showing extracts from the notes. So this is definition 1.1. Here's the kind of notation we use for a sequence of numbers. Okay, x1, x2, x3, x4, and so on. These are the elements of our sequence. And we zoom through some basic and interesting sequences that we might meet in mathematics. And this is where we're going to continue on now. There's a couple of important types of sequence that we might meet. These are arithmetic and geometric sequences. And these are ones which have a particularly nice form, particularly nice and consistent structure that makes them very easy to analyze in a sense. So an arithmetic sequence is one which always changes by a fixed set amount. Okay? So an arithmetic sequence will look like some initial term A, then the next term will be A plus D. So D is the difference between terms. Then the third term will be A plus 2D. The fourth term will be A plus 3D, and so on. Okay? Each term is just equal to the previous term plus D. Okay? Very nice, even, consistent, boring behavior, if you will. Okay? There's not too much that interesting that can go on with an arithmetic sequence on the face of it, although they do hide some very nice things. There's an important theorem which we discussed in second year number theory, which says, I mean, you might think these things are, you know, what interesting kind of stuff could go on in such sequences, but there's a proof, it's called Dirichley's theorem, that says every arithmetic sequence like that, as long as all of the numbers aren't obviously composite, for instance, let's say your A and D were both even numbers, both divisible by 2, then it's pretty obvious that every element in the sequence is divisible by 2, because you're adding together two even numbers. So in that case, everything's composite. But if your A and your D are what's called coprime numbers, if they don't share any common factors, then Dirichley's theorem proves that every such sequence, with a pair of parameters A and D that are coprime, every sequence like that contains an infinite number of prime numbers. So it's a very interesting fact, and suddenly arithmetic sequences don't seem so boring anymore, because there's something deep and mysterious there as a connection to prime numbers. Okay, so that's something you can learn a bit more about in the second year unit, number theory. So again, I'm just throwing terminology at you and just kind of learning some definitions. Second type of sequence is a geometric sequence. And a geometric is one which kind of, again, progresses in the same set fashion, but this time using the operation of multiplication instead of addition. So it's got some initial term A, and then the second term will be A multiplied by this fixed quotient R. Okay, this fixed multiplying factor R. The third term will be the second term, AR, multiplied by another R, so AR squared. The fourth term will be AR cubed, etc. If the sequence has that structure, it's called a geometric sequence. So arithmetic sequences proceed by fixed additions each time. Geometric sequences proceed by fixed multiplications each time. Here's a couple of examples. This, okay, that's not that illuminating an example. It's not that illuminating an example, perhaps, but the sequence of positive integers themselves can be expressed as an arithmetic sequence. It's got the first term 1, and then the fixed difference 1 each time that you're adding on. That's not really incredibly interesting. But the sequence of all odd positive integers, for instance, is also an arithmetic sequence, because there you're beginning with 1, then you're adding 2 on each time. 1, 3, 5, 7, etc. That's also an arithmetic sequence. A geometric sequence, well, for instance, we could look at all the powers of a half, say, 1, a half, a quarter, an eighth, and so on. So an is, given a nice formula there, a half to the power n minus 1. Okay, that's clearly a geometric sequence. Each term is this fixed multiple, a half of the previous term. Perhaps a bit more interesting, in an applied sense, if you look at the formula that governs the behavior of a kind of fixed investment at a fixed periodic interest rate. So for instance, you put some amount of money in a bank account, it's paying a set amount of interest added on every year, then this formula here tells you what the value of your investment is after n years. So P, which comes from the word principal, so principal is an initial investment. You put P dollars in a bank account after n years, if the interest rate is R%, this formula here tells you what the value of the investment will be after n years. Okay? It won't grow very fast these days because the interest rate is half of 1% operating at the moment, or that's the Bank of England base rate, so that's approximately what you might expect to get in a savings account. So it's not very good for savers at the moment. But this is clearly a geometric sequence of values. The value V1 after 1 year, the value V2 after 2 years, and so on. Okay? Each year's value is whatever was in the account at the start of the year multiplied by this fixed interest multiplier, which is the quantity 1 plus R over 100. Okay? So in the previous definition of a geometric sequence where we had that fixed multiplying factor R, well, in this interest rate example, it's 1 plus the interest rate over 100. Bit unfortunate I used the letter R there in both cases, but that's the way it is. Very often in mathematics, when you introduce new concepts and you look at examples of it, it's also good to look at negative examples as well. So for instance, this sequence, the sequence of elements which goes xn is 1 over n squared. So 1 over 1, 1 over 4, 1 over 9, 1 over 16, etc., etc. That is clearly, well, if you think about it a bit, it's not arithmetic, and neither is it geometric. Okay, the elements are not proceeding. They're not increasing by a fixed step size that's added on each time, nor are they increasing by a fixed multiple that's multiplied by the previous element each time. Okay, so that is neither arithmetic nor geometric. Now, from time to time, we will meet these terms, arithmetic and geometric, again. So we'll recognize them when we see them. Now, in the introduction lecture, we said we were going to be looking at convergence. We spent some time discussing the phenomenon of convergence in general. So that's going to be looking at, when you have an infinite sequence of numbers, studying the concept of this sequence converging to some kind of fixed limit. So as a bit of a stepping stone to that, we'll first think about one, maybe a simpler aspect of the long-term behaviors of a sequence, whether it's an increasing or a decreasing sequence. Okay. So, I mean, these terms, I mean, it's pretty clear what they mean. We would call, see this definition 1.3, we refer to a sequence as increasing if the elements are getting bigger. It's an increasing sequence. So if each element is less than the one that comes after it. And in the same way, we'd call it decreasing if each element is greater than the one that comes after it. Now, you can have, if you just say increasing or decreasing, maybe you normally mean that you have weak inequalities between them. So you could have an element of a sequence equal to the one that comes after it, and so on. But if you can change the language slightly, and you can talk about strictly increasing or strictly decreasing, which would be these definitions just replaced with strict inequalities. And here's where we're going to get into our first worked examples. So in the kind of setup where we are considering a sequence defined by some kind of formula, we might want to produce a bit of a rigorous argument to say whether the sequence is increasing or decreasing. And, well, here's two ways of approaching that. These are ways of working with the formula, defining the sequence, and trying to, in a nice, direct, rigorous way, establish whether the sequence is an increasing or decreasing one. Okay? And one way to do that is the difference method, which is shown here. And that's where you examine, in general, the difference between consecutive terms. So you try and write, so if you're dealing with the sequence ANs, you try and express this difference, AN plus 1 minus AN. That's the difference between a general term, AN plus 1, the difference between that and the term that came right before it, AN, in the sequence. If, when you express that quantity and simplify it as much as you can, if you're able to show either that it's always bigger than or equal to 0, or that it's less than or equal to 0, then you will have established increasing or decreasing behavior as appropriate. So if you can show that AN plus 1, AN plus 1 minus AN, if, for instance, you can show that that's less than or equal to 0, well, that's equivalent to saying AN plus 1 is less than or equal to AN. So that would be, what is it, a decreasing sequence. And if you can show the other type of inequality, you'll have established a increasing sequence. So that's one way to do it. The other way to do it is to think about the quotients of consecutive terms. Yes? Question? Well, we haven't got on to converging yet. So it could be converging as well. It could be not. So increasing isn't going to imply that it's convergent or divergent. You could have increasing convergent sequences, ones which are creeping up to their limit, increasing by ever smaller amounts. You can also have increasing divergent sequences. Well then, would you call that increasing or decreasing? Well, it's not consistently doing either. If your sequence is wandering all over the place and continues to do that, then it's not increasing and it's not decreasing. Yeah. So we're not saying all sequences are either increasing or decreasing, but it's just two types of sequences that we might encounter. Okay. But more or less equivalently, we could use a different method where we look at the ratio of consecutive terms. AN plus 1 divided by AN. Now there, you're not trying to make a comparison with 0, like we were in the difference method. There, we're trying to make a comparison with 1. Because a significant value for a difference is 0. That tells you whether it's going to be increasing or decreasing. But when you're looking at a quotient, the significant value is going to be 1. Whether or not this inequality is bigger than or less than 1. Whether or not this quotient is bigger than or less than 1. Because this would be equivalent to saying that AN plus 1 is less than or equal to AN. So again, that would be a decreasing sequence. Now this is, of course, just be a little bit careful. This movement, saying that these two inequalities are equivalent, it's not true always. It's a little... It's not true. Yeah, I have to be a little bit careful what I'm saying. This would only be true when AN is a positive quantity. If you multiply both sides by a negative number, remember you have to flip the direction of the inequality. So you have to handle these things carefully. Okay, so let's look at a first example here. This is example 1.1. I think this is our example 1.6. I think the working out of this is in the notes, but let's just reproduce it on the overhead just to talk through it. So here we're considering the sequence AN defined by, so the formula here is AN is 5 to the power n over n factorial. Does everybody remember what n factorial is? So if you have some number and you take its factorial, some positive integer, what you're talking about is m multiplied by m minus 1 multiplied by m minus 2. If you keep multiplying it by all the numbers, all the integers, all the positive integers down to 1. 10 factorial is pretty big. 10 by 9 by 8 by 7 by 6 by 5 by 4 by 3 by 2 by 1. So let's try and do the quotient method here. So we'll examine the ratio AN plus 1 divided by the term that came before it, an. And you see, we're not talking about one particular term in the sequence, we're talking about a general term. So we're simultaneously here talking about this quotient throughout the whole sequence. We're working in general. So an plus 1 is 5 to the n plus 1 divided by n plus 1 factorial. That's the term an plus 1. Then we're going to divide it by an. So that's the same as multiplying by the reciprocal, turning the fraction upside down. So n factorial over 5 to the n. And we're trying to compare this to 1. Now, looking at it now, it looks a bit complicated. Can't quite see whether it's bigger than or less than 1. But of course, because these are powers of 5 and factorials, that's all about operations of multiplication. And I've got them all on the top and bottom of the fraction. So there'll be lots of cancellations that I can do here to simplify this one. In particular, if you look at the factors of 5, you got a whole load of 5s on the top and a whole load of 5s on the bottom, but there's one extra 5 on the top. You've got 5 to the power n on the bottom, 5 to the power n plus 1 on the top. So overall, what you're just left with there is 5. All the others cancel out. The factorials, well, here you've got n factorial on the top of the fraction, which is n multiplied by n minus 1, multiplied by n minus 2, etc., multiplied by all the positive integers down to 1. And on the bottom of the fraction, you've got n plus 1 factorial, which is n plus 1 multiplied by n, multiplied by n minus 1, etc. When you examine those two factorials, you see that every factor of the n factorial is contained in the n plus 1 factorial. They're almost the same. It's just that the one on the bottom has an extra factor at the front, which is n plus 1. We get this quantity, 5 over n plus 1. And we want to make a comparison to 1. If we're going to determine whether this sequence is increasing or decreasing, we want to say, is this bigger than 1 or less than 1? Well, okay, the fraction 5 over n plus 1, it can be both. Mostly, it's going to be less than 1. But for a little bit at the start, it's going to be greater than 1, isn't it? So this is so we can say 5 over n plus 1. This is going to be greater than or equal to 1 for the values of n between 1 and 4. Okay, so just for a few bits at the start, this quantity is going to be bigger than 1. But then most of the time, really, for the rest of the sequence, it's strictly less than 1. Okay? So 5/6, 5/7, 5/8. So we're then into quantities less than 1. This is you might have seen this notation before. This is a way of, like, rather than saying this thing is greater than 1 or this thing is less than 1, splitting it up into different cases. So this is sometimes called the cases notation. We've got one statement for some cases of n and another statement for other cases of n. Now, what does this say about our sequence? Remember, what this quantity here is, this is an plus 1 over an. Is greater than or equal to 1 or strictly less than 1 for the same conditions here. So i.e., we're saying an plus 1 is greater than or equal to an for a little bit at the start, but thereafter an plus 1 is going to be strictly less than an for every n bigger than or equal to 5. So it's increasing for a short time at the start, but really, the sequence as a whole, after the start, it's really a decreasing sequence. So that's an example of using this quotient method to look at the quotient or ratio of consecutive terms of the sequence, simplify the expression, compare it to the appropriate thing, which is 1, and declare whether it's bigger than or less than 1, and hence reach the conclusion about being increasing or decreasing. Just bring up MATLAB here. It might take a moment to. So this, I mean, this here is a kind of is a proof, if you like, a rigorous mathematical argument considering these things in general. But on the other hand, we can also, while it's not a proof that the whole thing is increasing or decreasing, but we can also get a pretty good idea by investigating the sequence and looking at a load of terms and just kind of visually doing some calculations with it and trying to see how the sequence is behaving. So I'll just wait for this to come up. Okay, this is some kind of arbitrary gap of time here, waiting for this to come up. I will show you examples using another mathematical system called SAGE throughout the course as well, but since you're getting started with MATLAB at the moment, I'll show you this here. So, yeah, so I did pre-prepare a little bit of code here. So this little bit of code investigates, well, not that sequence, but let's change this. So what was it? 5 to the power n, 5 to the power I divided by factorial I. I won't go up as far as 100. I'll just go up, say, 20. Factorials get quite quick. Okay, I think, yeah. So this is a little program. Let's just talk through what it does. This command up at the top, s equals bracket bracket, that sets s to be an empty vector, an empty list, an empty row vector. And then we have a little for loop. Now, you mightn't have come to these programming constructs yet in the MATLAB course, but you will soon enough. I'm just showing you first example here. So this is a for loop. It's saying it's going to loop through the values of I from 1 to 20. And each time, it's going to take s and it's going to redefine it. Now, you see what the structure here is I'm redefining s, square brackets, and I'm putting s again. So that means I'm going to take the list s, I'm going to make it equal to itself, but I'm going to stick on an extra element. And the extra element is described here. This is the one that matches this example. It's the next term in the sequence, so it's 5 to the power I divided by factorial I. Okay, so with I being used as the index here instead of n. Then, so this loops through these instructions 20 times. Then, by issuing the command s, it'll print out the list s. Then finally, this plot command will show you a picture of it. So it's a little program in MATLAB there. We can run it. And it gives us a nice plot of values, and it does indeed, you know, it backs up our analysis there. You see the sequence increasing in values for the first few terms when you get to 5, so then you reach equality around between position 4. See, the next element is exactly the same, but thereafter it decreases. And this output that appeared in the command window down here, this is the output down here from this s command here. So when you just type the name of a variable in MATLAB, if that occurs in the program, MATLAB will by default try and print out the value of the variable. This is a list of values, yeah, 1 through 17, 18 through 20. So it starts off 5, 12. So you see it increasing for a bit at the start, and then after that it decreases. That's a nice simple example MATLAB program. And you can certainly see how you can start to adapt it to match other examples. By putting in the appropriate thing there, you can change it and get it to do this similar operation for other sequences. And if you change this upper limit of 20 in the loop there, you can get it to give you more or fewer elements of the sequence. Okay. Soon enough, hopefully, you'll be meeting the people in the linear algebra and programming skills will be taking you through programming in MATLAB. Okay. So let's go have a look at another example. So we'll take this example. This isn't in the notes, so this is just on the screen. So we'll consider the sequence of elements Sn defined by, so what have we got here? 3n divided by 4n plus 1. And we want to apply this approach of using the difference method or quotient method to try and see if we can prove that this is increasing or decreasing. The only reason I'm popping this off is because I should be trying to remember to record the screen when I'm doing stuff on the screen. So you can revisit this later on. Okay, now this is a more kind of what we call a linear example. See, the previous example was 5 to the power n, and the factorials, that was very multiplicative. The operations going on were multiplication all the time. And then when you put those kind of things in a quotient, they tend to simplify down nicely. This one isn't necessarily, this looks a more kind of a linear thing. The dependence on n is just in a linear way. So I'm going to try the difference method here. So we'll consider the difference between consecutive terms, neighboring terms, if you like. So we'll look at Sn plus 1, and we'll examine the difference between that and Sn. Term that came right before it. And here's where you just have to be a little bit careful, proceed carefully. What is Sn plus 1? What is it not? It certainly isn't a fraction with 3n plus 1 on the top. What's on the top of the fraction for Sn plus 1? 3n plus 3. Yeah. Careful when you're substituting in new values for the index. So here's the formula that defines the general element of the sequence. But if we put in a modified index, so the index n plus 1, that has to take the place of n here. So it all gets multiplied by 3. The numerator here is 3n plus 3. And what's the denominator? 4n plus 5. Good. We replace this n by n plus 1, so it becomes 4. That's our Sn plus 1. Then we subtract Sn. So Sn is straightforward, 3n over 4n plus 1. And we have to make the right comparison. Is this larger than or smaller than 0? It's not immediately obvious looking at the fractions. They're different fractions. They're not immediately comparable. It doesn't leap off the page at me. So one way to try and simplify this and make a good comparison, well, rather than looking at the difference between two separate fractions, is to try and bring them together to a single fraction. How do you do that? How do you do that? Of course, well, you put them over a common denominator, and the simplest common denominator is going to be the product of the two denominators. And then the new numerator will be 3n plus 3 multiplied by, you do this cross multiplication stuff, multiplied by 4n plus 1, and then we're subtracting 3n multiplied by 4n plus 5. Okay, so that's the way we take a difference of two fractions, write it as a single fraction. Now, what kind of thing might we do here? Well, keep in mind, we want to compare this to 0. Decide if this is larger than or smaller than 0. Now, how do you tell if a certain fraction is bigger than or smaller than 0? Well, you need to know what the sign at the top is and what the sign at the bottom is. Because one positive thing divided by another positive thing is going to be positive. One negative thing divided by a negative thing will be positive too. But if the top and bottom are of opposite signs, overall the fraction is going to be negative. Okay. So our task here is for the top to decide if that's positive or negative, and for the bottom to decide if that's positive or negative. Which one is obvious? Bottom. Why? Is it positive or negative? Why? Kind of obviously not negative, isn't it? Yeah. So yeah, the bottom has two quantities multiplied together, and are both of the quantities positive? Yeah. Why? Because, well, I mean, they don't have to be, you know, if n was a negative number, they could be negative. But what is n? N is the index in our sequence, and, well, quick adjustment. The index is going to start at 1 and then proceed to the positive value. So n is only ever positive. Therefore, 4n plus 5 is positive, 4n plus 1 is positive. So straight away, we can recognize that the denominator is positive. We'll make some remarks about that in a moment. But we certainly don't, there's no need to go expanding out that bracket there. The numerator is a bit less obvious. Maybe we do need to expand it out just to see what's going on, because there's differences. So when you multiply this out, of course, what are you going to get? Well, you get a 12n squared from here, then you get a minus 12n squared. There's no n squared. How many n's are there? There's 12n plus 12n plus 3, 15n here, minus 15. There's no n's in it at all. So what's left? 3 by 1, 3. Okay, well, that's great. 3 positive or negative? Positive. So it's all positive stuff. Positive top, positive things in the bottom, multiplied together get positive. So this, we can say, certainly strictly bigger than 0, but a little bit of justification since n itself is strictly bigger than 0. Yeah, you do need that, because if someone just looked at you claiming that this is bigger than 0, they say, well, how do you know? Maybe if the n's are negative, it might be negative. But the n is always positive, so this is certainly 0. Okay, at this point we have to remember where we were and what we were doing. Okay, so we now lose interest in all this stuff in the middle, and really we're just, all we want to record is just the top and the bottom. What we've shown is that the difference between neighboring terms is positive. So rearranging the inequality, i.e., we've shown that Sn plus 1 is strictly bigger than Sn. So it's an increasing sequence. Agreed? And there's no qualifications about for some values of n it's doing this, for other values it's doing that. And the conclusion is for always for every value of n it's bigger than 1. And that's the relevant range of n. Okay, any questions about that, or queries, or questions about the way I've laid it out there? And you'll get this kind of stuff a lot from me about you should adopt in all the stuff you do, even if you're just working through things yourself, you should adopt good mathematical writing style. And that means these little introductions and conclusion statements are important. They're part of the argument. They're just as important as all the algebra, in a way. Okay? Certainly if you want to take this work and show it to other people. I mean, if all you include here is just this stuff in the middle, you know, and you show it to someone else, they probably won't get what you do. And if they lose the question sheet, then they really won't get, they've nothing to compare it to. So try and make the work you produce a kind of complete story from start to finish. So we're considering this sequence. I tell you what I'm going to do, I do it, and I draw the correct conclusion. So it kind of stands alone as a complete piece of work. And it applies equally if you're just making these notes for your own benefit, because when you come back to read, why do you bother to make notes so that you can use them in the future? And when you come back to look at your work again, well, you've forgotten what you were doing beforehand. So you do need all these explanations to tell you what exactly. And ultimately, like in assessments, in coursework, some exams, you're going to have to be writing for other people to read. And then in the longer term, you're going to be applying your mathematical skills, communicating them to others in some shape or fashion. So good quality mathematical writing is important. And one aspect of that is always including adequate English or whatever language, adequate explanations in and around the mathematics, in and around the symbols. Okay. Okay. Let's get back on the computer a bit. So what I'd like to do now is to show you the tutorial question sheet that you're going to be working on. So some of you will have your tutorial this week. Sorry, today. And the others of you will be having it on Friday. It's probably easier actually to do this copy. Yes, so the relevant exercises that apply for this week from my sheet would be questions 1, 2, and 3. So just to introduce them to you, what's going on here is in question 1, well, there's just a bunch of example sequences, and these are the easiest questions on the sheet in some ways. Just getting you used to working with the formulas, reading the notation, and so on. So, quite a basic exercise to get started is just to take each of these sequence definitions and develop the first 5 terms of them or so. Okay, just be comfortable with evaluating the formula and reading the definitions. So we've got some formula type sequences, and then we've got some recurrence relations now, where the element in the sequence is defined in terms of the previous ones. Okay. And then this question 2, it says for each of the elements, for each of the sequences in question 1, find an expression for the 2m plus third element. And what am I talking about there? So for instance, in question 3, the kind of thing I'm talking about is, so to see this sequence here, dn, what I'm meaning is, what does d2m plus 3 look like? That's the 2m plus third, depends on m of course, 2m plus third element of the sequence d. Well, take the formula, finding d, replace n with 2m plus 3, and do any kind of simplifications that you can do. I include this kind of exercise in here because it's a common mistake, or it's a common place where people slip up. When they're doing work with sequences, and when we come to be doing more sophisticated things with sequences, very often you have to jump around in the sequence and refer to elements where the index is like some formula of a basic index. And an easy slip up to make is to not make the substitutions correctly, or to misidentify this element of the sequence. There's nothing special about 2m plus 3, something chosen off the top of my head, but it's a reasonably complicated formula for a new index. Sorry, that's question 2. That line should be emanating from. And then question 3, I want you to start to try and assess these sequences and find out whether they're increasing or decreasing. Now, you may have varied success in being able to do it, these simple proofs, but to try and do these arguments based on, like we've been doing here, based on the difference between terms or the ratio between terms, assessing these and trying to generate proofs that they're increasing or decreasing. Now, when you come to the recurrence relations will probably need other kinds of argument. So conclusions using the ratio or difference of consecutive terms, or otherwise for the recurrence relations you could add on there. The straightforward difference or ratio approach mightn't apply to the recurrence relations. And this little computer symbol beside this question also is just a visual reminder that use of a calculator or a computer, just like we did with the MATLAB plots over here. Oh, it's gone already. You might find that useful as to get, to tell you what the right answer is, so to speak, whether the sequence is an increasing or decreasing. Okay. Now, looking ahead to next week, in my lecture with you next week, what are we going to be doing? Well, we're going to get on and start to talk in detail about this convergence phenomenon. Okay, so we spent some time introducing it in general scientific setting, in our first lecture yesterday. But we're going to get quite detailed and quite mathematical. Start to look at the proper formal definition of convergence, and also start to look at some of the theory that we're going to build up. And the main part of theory here is embodied in the algebra of limits theorem. It'd be good preparation to read ahead through this section, and particularly focus on theorem 1.4, the algebra of limits theorem. We're going to be proving this in a lecture or two's time, and this is telling us something about the concept of convergence itself. So not just looking at loads of particular examples, but actually proving something in general about the whole phenomenon of convergence for sequences. Okay, so best of luck with your tutorial questions this week, and I'll see you next Wednesday.